Hello, thanks for coming to the pipeline wall thickness selection course. A pipeline wall thickness, this is the most important parameters for pipeline projects. Today, we're together to go through how to select the pipe wall thickness. This is the contents of this course. The first one is the importance of wall thickness selections, followed by how material or pipeline will fail. This is the fundamental for the design criteria. After that, we will focus on these four design criteria. The first one is bursting due to the internal overpressure. The second one is local collapse due to the external overpressure. Then we will follow by propagation buckling criteria. And the last check is the combined load check for relay project, which is very common in the North of Norwegian Sea. I will also touch a few parameters in the wall thickness design, which is not common, or maybe not well explained in design codes. The last one is the considerations beyond the code. This is really a lot of experience involved, but it's also important for pipeline wall thickness selections. Why the pipeline wall thickness selection is important? Because wall thickness is the main barrier against failing of pipelines. If the wall thickness is gone, then the pipeline is gone. And wall thickness is also the most important parameter for the material resistance or capacities. In the limited state design, one side is the load, one side is the material resistance. So wall thickness is the basic parameters for material resistance. And wall thickness need to be frozen or decided in the very beginning of the execution phase of the project, or even in the feed phase, due to this very long lead item of line pipe procurement. It's normally happen like 2 years before the pipeline installations. And wall thickness also affects almost every aspect of the pipeline engineering, from bottom stability to free span to troy impact, pipeline global bucklings, installation analysis, vessel trips, the ECA, etc. But in the beginnings, you may not have the time to perform every engineering checks before you frozen wall thickness. Therefore, experience is important to select the proper wall thickness. And it needs to balance the need from different engineerings. Before we go through the details of the design criteria for pipeline wall thickness, let's record the fundamental of material failures. Von Mises yield criteria is still the applicable material failure criteria for metals, which is the ductile materials for pipelines. When we look at the left plot here, this is a 3D plot for Von Mises yield criteria. And in the pipeline systems, normally the shear stress is quite low, or can be negligible. Therefore, it's often reduced to a 2D plot here. And one direction is the hoop stress directions. Another direction is the longitudinal stress, or maybe actual stress directions. If this pipeline stress beyond the solid circles here, we consider material is fail. And this is a typical test for tensile test results. We apply the tensile force of these materials until the material breaks. Then we can plot the stress strain levels of the metal, and we can get the yield stress according to the definitions. What are the failure modes for pipelines? Here is a list to show the different failure modes from burstings. And the bursting is dominated by the internal overpressure, like here. The hoop direction or hoop stress is the dominating stress, causes the material to fail. We have system collapse, which is caused by the external overpressures. So the external pressure will try to crush the round cross section into flat ones. And when collapse happens, and it may propagate through the whole pipeline actual directions, and we call it propagation bucklings. And pipeline can also have this local buckling due to the combined loading, which you have actual force, bending moment, internal external pressures, and it will like have a local buckling. And there's also another tool called fatigue, failure or fracture failures. And fatigue is normally is a screen or conservative approach. We don't know the detail of the welds. We estimate how long the welds can have, how many cycles, and what the cumulative fatigue can be in the welds. And the fracture mechanics of fracture failures is more a detailed analysis. So we know from acceptable defect size, and we can calculate how much this crack can propagate through the different life cycles and accumulation of fatigue, and to what extent it will break the pipe. And this failing modes we call out limited state or fatigue limited state. There's another called service limited state, which is like this one. One is a denting. The denting can caused by drop objects or a trawler. We can also have a pipe ovalization, which is out of roundness. Typically in readings, your pipeline will become a little bit flatter compared to the original status. We also have this called ratcheting. Ratcheting is a accumulation of plastic strings during different phases, like installation or lateral buckling in operations. Now we go to the more mathematic or the detail of the how to select the pipeline wall thickness. One is the most important is this bursting, or we call pressure containment. And bursting is caused by higher internal pressures. And hoop stress is a key parameter for the bursting design. And here is a pipeline in the sea waters. Normally the internal pressure is higher than the external pressures. And when we cut to the pipeline cross section here, we have the hoop stress direction is here. And according to the force balance equations, if your hoop stress here times your wall thickness here, one wall thickness here and one wall thickness here, so your hoop stress times 2T should be equal to the internal pressures times the internal diameters minus the external pressures times external diameters. So this is the basic equations for hoop stress. And in reality, hoop stress has a little bit of variation across the wall thickness here. So it's not a constant values. But this assumption is quite reasonable if the wall thickness is quite thin. Say if the D over T, the diameters over the wall thickness is larger than 15, is this considered a thin wall thickness? The sigma, the hoop stress is quite constant across the wall thickness. Different codes have different hoop stress formulas. The general formula is like hoop stress equal to internal pressure minus external pressure times the D star, then over 2 times the T star. And this D star in different codes, or T star in different codes, have different expressions. Like in the SMIC code, the D star is D nominal, which is outside diameters. And the T star is the T nominal wall thickness. In API, the D star becomes D nominal minus the T nominal, which is the middle wall diameters. When we go to the ISO 31833, then the T star becomes the T minimum wall thickness. And T minimum wall thickness is the nominal wall thickness minus the fabrication tolerances, minus the corrosion tolerance, and minus erosion tolerances. And when we go to the DV STF101, which is the main kind of design code for our subsea pipelines, then the D star becomes the middle wall diameters, and the T star becomes the T minimums. So it's important that we don't mix code when we start to design wall thickness. We need to stick to one code. They have different expression for the formulas, and they have different safety factors. This is a level straight design approach, like the SME code or PD8010 approaches. Is that your hoop stress need less than your yield stress times factors, like usage factors. And this is a typical stress strain curves for pipeline materials like carbon steels, and you have a yield strength in like 0.5% of strain, like here. And this is your yield strength to be used in the design. And if you have usage factors, then you have proportion limit somewhere here. So this is the basic level stress design approach for bursting pressure containment. This is a limited state design approach from DNV. And DNV did a lot of bursting tests, and they concluded this is a better formula to represent the hoop stress. Consider even the 6-bore pipe, and it is the internal pressure minus external pressure times the D star over by 2 times star T star, and it should be less than a factor times the yield or tensile stress. And this formula is a typical limited state equations. One side is a load and one side is material resistance, which considering the material factors and the safety class factors. And not only for the operations in here, it's also for the system test pressure conditions. And here is the pipe capacities, and this is not only is the yield strength, but it's also consider tensile stress. If the material strength is high, the tensile stress may become dominating instead of yield strength. And this 2 over square root 3 is considered the factors, like here. Another important consideration for bursting is this bursting capacity reduction due to the high compression actual true force. This normally happen for buried high temperature, high pressures, or inner pipe of the piping pipe systems. And here the reason. The left picture is the von Mises failure criteria, and normally we have the hoop stress and have certain factors times the yield strength here. However, if we have very high compressive actual force in the in-place conditions, then our allowable hoop stress can be reduced because we have a high longitudinal or actual force here. And DNV published a GIP on the consideration how to consider this bursting capacity reduction due to the high compressive force. And my opinion is, for a normal project, 5 to 10% should be good enough. But for special cases, special consideration may need to be. This also depends on your lateral buckling strategies. Now we'll talk about the local buckling, which is one of them is a system collapse. System collapse is caused by external pressure, especially when the pipeline is empty. So typically in installation phase. And collapse is not governed by a single equations, and there are 3 types of collapse mechanisms. The first one is called elastic collapse. It's more like a bending moment for thin shell bucklings, and the pipeline will lose its stability. This was developed by the Timoshenko's elastic series. And here's its equations. The required external pressures to cause an elastic collapse is equal to relevant to the wall thickness, the pipe diameters, Young's modulus, and the Poisson ratios. For the people who have more interested, refer to Timoshenko's book. The second collapse mechanism is plastic collapse. This is normally for thicker pipes. The yielding dominated before elastic bucklings is more like a force to yield the cross-section here. This is equations to relevant to the external pressure for plastic collapse and to the relevant to the material yield strength, relevant to the fabrication factors. These fabrication factors basically is a material strength loss due to the pipe manufacturers, and relevant to the thickness and the pipe diameters. And the third mechanism is something between the elastic collapse and the plastic collapse, something in between here. So it's called transition collapse. DV combines all these three mechanisms using an empirical transition equations based on theory and based on full-scale test data. This is like an interaction formulas that blend the elastic and plastic series and induce the imperfection factors, which is pipe ovalities, and also a diameter to thickness effect, which is d over t here. The pipe ovality normally is like a 3% maximum in DMV codes, but it can be over this 3%, but the more analysis is required. And this equation looks very complicated. There's one section in DMV provide a step-by-step how to solve these equations. And this equation has been validated by a lot of testing data. When system collapse happens, and then it can propagate along the pipelines. Look at the letter figure here. So we have a starting with a collapse here, and it can go through the actual direction of the pipe, and will stop somewhere with the thick sections here. So this is called propagation bucklings. And normally the propagation buckling pressure, the required pressure for propagation buckling is less than the collapse pressures. So it's very likely that the collapse is triggered by drop objects, lateral buckling, or trawlers, and they start to propagate. And this is the typical equations to calculate the propagation buckling pressures. And we also have a fabrication factor here. We have yield strength here. We have a T over D ratio here. But in reality, when we calculate the required water thickness for propagation bucklings, we normally don't increase the water thickness because of propagation bucklings. We're using called buckle arresters, either a thick section of a pipe or a clamp to reduce the risk or to reduce the consequence of propagation buckling. After I have done the propagation buckling checks, if our pipeline is relay, it's very common in Norway, Norwegian Sea or North Sea, and we have to check another one called local buckling for combined loading for reelings. And because the pipeline, if you're using relay method, the pipe will experience very high stress or strain on the reel or on the liners. So we have to check whether the wall thickness is thick enough against the collapse. And this normally, because happen in the reel, we call displacement control condition, DCC. And the equation is your design compressive strain should be less than your characteristic bending strain resistance over your material factors. And normally this check is a conservative and a screen check. If we can using a finite element analysis, normally it can optimize the required wall thickness. After we have go through the 4 modes, we need to check some of the parameters and what does it mean in the previous checks. One of them is called characteristic thickness, and we have checked the bursting, system collapse, propagation buckling, and combined loadings. And the first two are using wall thickness T1. The second two, they're using wall thickness T2. And then what is the difference with T1 and T2? Here is difference according to DNV definitions. Prior to operations basically is installation and the temporary phase. The T1 is the nominal wall thickness minus your fabrication tolerances. And in operations, it further to minus the corrosion allowance and the erosion allowance, which cause wall thickness loss. But for T2, is only consider nominal wall thickness prior to operations, and then you consider nominal wall thickness minus corrosion and erosion allowance. Why we have differentiate the required wall thickness differently? My understanding is like for bursting and the cleft check, every orientation of the pipe cross section is important. For example, you have the thinnest wall thickness at the 3 o'clock of your pipeline cross sections, and if you have very thin wall here and the 3 o'clock location will fail. But for propagation buckling and combined loadings, and not only normally even you have a weak section at 3 o'clock, you have a thick walls at 6, 12, or 9 o'clock. So you have your whole cross section capacity will not be kind of governed by the minimum wall thickness. Therefore, normally using T2 to do the capacity check and not a T1. The bottom two figures show the typical wall thickness tolerances for line pipe, and for seamless pipe, normally you have a higher wall thickness tolerances. And if you have a supplemented D, which D is mean dimensions, you have minus 10% from fabrications. But for welded pipe, because the welded pipe is from a plate have quite accuracy thickness from the mills. Therefore, if a better wall thickness tolerances for welded pipe. Another parameter is called characteristic yield stress and the characteristic tensile stress. Now, why is not called the specified minimum yield stress or specified minimum tensile stress? We call characteristic. This is for consider the material strength derating due to the temperatures. When we look at the right plot here, for super duplex or duplex materials, and you have quite high material derating when the design condition, the design temperature go up. And the red line shows the carbon steel and 30% chrome line deratings. After 50 degrees C, your material start to have derated yield strength or tensile strength. In addition to the material derating due to temperature, you also have this alpha U, which is the strength factors. These strength factors is described as what is your standard deviations. If you have a narrow standard deviations, which means fulfilling the supplementary U requirement, then you can using 1.0 factors instead of the common one, 0.96. In the collapse and propagation buckling check, we also have this called material fabrication factor, alpha factors. These fabrication factors is to consider the material strength loss from the pipeline manufacturers. And you have the radial stress, you have pipe ovalities, you have compressive yield stress loss. Therefore, you have a lower fabrication factors if you have a UE pipe. For example, here. So the UE will start to fabricate a pipe from a plate, then you bend into a U shape, then you go to O shape, then you start to weld them on the seam welds, and you try to expand it. During the whole process of UOEs, you will have radial stress, you will have ovality, and you have a compressive yield strength loss. But for another method called JCO, you start put like a J shape first, then you put the form into a C shape, then you put the O rings and weld them. After that, you compress them into the opposite directions of expansions. Then you have a better fabrication factors, which is 0.93. And if for a seamless pipe, you don't have that radial stress, ovality, or compressive yield strength, then you have fabrication factors 1. In the reading screen check, which is combined loadings, we also have this parameter called string hardening factors. What is the string hardening factors? So this curvature, the red one, is a typical string stress curvature for pipe materials. And we have a elastic stress of strings here. And after the yield point, the material start to become harder. You have increased stress when the string increases until you have a breaking point here, which is a tensile stress location. So the maximum value of this one is indicated the yield stress over the tensile stress and the maximum value. This is called maximum string hardening factors. And when we put it into the equations, you have also the Gauss-Weld factors. We can introduce it later. And we also have the called alpha P, which is the pressure factors. The pressure factors is if you have internal pressure inside the pipe, and you can prevent it from collapse. So this is a positive effect to increase the material resistance against collapse. And you also have the alpha material factors, and the material factor is a kind of delayed hardening for materials having a Luden plateaus. What is the Luden plateaus? Is when your pipeline start to have higher strings. Instead of hardening directly, you have a flat part here before it's hardening, and this flat part is called Luden plateaus, which you have a delayed hardening effect, which is a negative effect to the pipe capacities. Therefore, we have these equations have the material pressure factors, material factors, and Gauss-Weld factors to have a better understanding of the material capacity. These are Gauss-Weld factors. Research has found that the compressive strain capacity reductions can heavily depend on imperfections of the Gauss-Weld, especially for higher D over T pipes. Therefore, when you have a D over T higher than 20, then you have a decreased capacities until if you have a very thin pipe, the D over T 60 is really very thin. You even have 60% of your string capacity against the collapse. So this is called Gauss-Weld factors. And there's also a series of supplementary requirements from DNV. One is called supplementary D. This is an additional requirement for pipe dimension tolerances. Basically means with supplementary D, you have a tighter tolerance for pipe overall diameters, you have a tighter tolerance for wall thickness, you have a tighter tolerance of out of roundness. You even have a more often inspection frequencies. So this is called supplementary D. And for reading projects, you need to request the metal have a good plasticities. That's why we have this called supplementary P requirement. So yeah, this is required for reading projects. We also have the supplementary S. This is additional requirement for south services, like for carbon steel pipe. You have a special requirement for material chemistry components, and you have more requirement for HIC, which is hydrogen-induced cracking, and SSC, which is sulfur stress cracking testings. You also have the supplementary F, which is fracture arrest properties, and this is very common for gas pipelines, which you need to test for the choppy V-notch impact energy. Another one we already mentioned is called supplementary U. This is the additional requirement for higher material strength utilizations, and this is to ensure all the pipe yield strengths are above the specified minimum yield strength, even in the different temperature conditions. Therefore, supplementary U, sometimes if you have a higher design temperature, you have to do the test for a few different temperatures, and it's quite demanding for pipe mills. So sometimes pipe mill is prefer to have the pipe without supplementary U. We have already gone through the basic principles for choosing wall thickness, which is the bursting, the collapse, the propagation buckling, and the required reading screen checks. And this shows how we have been checked. Like we have, this is a stinger or maybe a reel. This is a kind of displaced controlled conditions. And we have propagation buckling during installation. Normally the pipeline is empty. We have a collapse and bursting in operations. But how about the other status, other failing modes? We have global buckling, we may have free span, we have the installation, we have like the sag band, we have high installation loads. Do we need to check this scenario to see whether the wall thickness is good enough? Normally the answer is no. Then the question is why we don't need to check the required wall thickness for the other scenario, the installation, onboard stability, free span, global buckling, walking or trolling. The reason is because we have different control methods in the other checks. For example, for installations, we also need to check this fatigue, fractures, we need to check combined loadings, we need to check the overlization or displacement. But the main control method is not to change the wall thickness. It's more like using equipment, increase the tensions, increase the buoyancies, and using the different installation method, like we using radial curvatures or to have a higher layback to reduce the sag band stress. So we have a different control method for installations. And for onboard stability, normally we don't check increase the wall thickness for the carbon steel because that will be a very expensive solutions. We're using like a coating or C-band interventions. C-band intervention normally including like rope dumping or trenching to bury the pipe to keep the pipe stable. Same for the free span, global buckling, walking, and trollings. The wall thickness will have an impact on this analysis, but the main control method is not to change the wall thickness, it's to using the other method to control it. And other methods normally are more economic, cheaper solutions compared to increase the wall thickness. Therefore, for wall thickness selections, we may need to think about the later one, but normally the late engineering will not affect us to select the wall thickness. The following slides is really like a consideration beyond the codes. We have the 4 basic checks we need to perform, but besides these 4 checks, what are still other things we need to consider when we consider wall thickness calculation or selections? One is the material selections. Before the wall thickness selections, what type of pipe material to be chosen? The material engineer is responsible for that, but the pipeline engineer can also contribute. And normally we consider carbon steel is the default one for pipe, if the corrosion allowance is reasonable. What is a reasonable corrosion allowance? Is less than 10 millimeters. And if the material grade is like DNV 450, which means the specified minimum yield strength is 415 megapascal. This is the default ones because it balances the required the material strength for design installation and also the welding requirement. The higher the yield strength, the more difficult for weldings or the welding quality and welding speed. But the lower one, you have a lower strength, it's bad for installation or the in-place conditions. For bundle project, the carrier pipe may choose using a lower material grade because the installation method is normally tolling, so may not be so demanding on the material strength. And also for the HFW pipe, which is high frequency weldings, and they have a more wider range of minimum yield strength to the maximum yield strength. That make if you're choosing 450 for the HFW pipe, you may have a very high yield strength as average, which will create a additional challenge for weldings. Then you may choose a lower grade. The other topic is CI materials. Like we mentioned, if the corrosion allowance is reasonable, less than 10 millimeters, then the carbon steel is a default one. However, if the corrosion allowance is more than 10 millimeters, then CIA pipe is recommended according to ISOs. And the CIA either clad or liner, there's two options for it. Together with the carbon steel, this is a good combinations because the carbon steel don't have the HISC issues, which is hydrogen-induced cracking, and the internal liner has good corrosion resistance against the contents. And we have three types of CI materials which are common. One is 625, one is 316L, and one is 825. 625 is expensive materials, but it's very high quality against the corrosions, including seawaters. Therefore, normally for like short spool materials, we use the 625 clad. Then you don't have worry about the seawater like go into the pipe during the installation or tying operations. This gives you a lot of flexibility for your offshore schedules. 316L is cheaper, but it need most likely you need the pre-qualifications against H2S, the South Service environment, and this test normally takes like 3 to 6 months. And if you're using 316L for spool materials, you need to flush the seawater within like 20 to 60 days. So it's not against seawater corrosions. And the CI material 825 is something between 625 and 316L. What is the difference with clad or lined pipe? The difference with clad or lined pipe is the clad pipe is you put two plates together. One is a carbon steel pipe plate, one is the liner plate. Then you band them together, and you weld them metallurgically bonded them, weld them together before you bend into a pipe. So you can treat this one as a one material for pipe. But the liner pipe, one is called booby pipe, one is called gooby pipe, because it's a line pipe. Liner will wrinkle because it's only like a mechanically expanded. Basically, you insert a CRF pipe into a carbon steel pipe, then using pressure to expand it. And only the pipe ends are using metallurgically overlaid welds. But the majority of the pipe, you only have a liner inside it. So during installation, if you have a high strings, the liner is easy to be buckled, like shape here called wrinkling. Therefore, most likely you need like internal pressures during installation to increase the liner capacity against the collapse. And groove pipe is a new technology to develop by Buttings, and the groove pipe is you use a glue to stick the liner into the carbon steel, but it's much cheaper than the clad pipe. So the groove pipe has been qualified for certain applications. What are other common pipe materials? One is the 13% chrome pipe. This is a solid CIA pipe, have a higher strength. Normally the minimum specified yield strength is 550 megapascal, and it's cheaper compared to the other CIA pipes. However, HISC is a challenge, especially for single pipe with reading applications. I think CIA pipe may consider good to be an inner pipe inside the piping pipe systems. But you still need to have in the EC analysis, you need to have a proper testing to evaluate how the crack will propagate on the environment. So this is a challenge for you need to have good enough time to test this 13% chrome pipe under a certain environment. And also we have 22% chrome, which have good resistance for internal corrosion, but not for seawaters. And this is quite common for structural pipings, like the subsea production system, like a manifold, Christmas trees, the piping, use 22% chrome. And it can also be used for like spools, flanges, normally for short section or pipe, not for a long pipeline because it's really too expensive. And they also have a concern of hisk. You also have 25% chrome materials. It's similar to 22% chrome, but more expensive. It's against the water corrosions, so give you more flexibilities offshores. The reason we have so many materials is really for it's the price and it's the anti-corrosion abilities, and you need to find a good balance about the cost and the benefit. So this is like a magnitude compared to a seamless carbon steel. How about the other pipes? The price look like, and this is only like a gut feeling, like numbers, ballpark numbers. For the quantity definitely have a big impact on the price. So you still have to check each time you check the price with the mills for update the informations. This is also the kind of pipeline procurement part, the manufacturing method. We have like different manufacturing methods. We have high frequency welding. We have the UE pipe. We have clad. We also have like coin and the seamless. Due to the manufacturing method, you may have a limitation of the pipe OD or wall thickness. So this plot shows the normal range for where certain pipeline diameters and the wall thickness or the kind of manufacturing method will suitable for. Normally the standard APS size, like standard pipeline OD and standard wall thickness, are generally more cost effective than the non-standard size, because the manufacturers and mill have the standard tools for the standard wall thickness and pipeline ODs. If you have a big quantity of it, they can modify or change the tooling to manufacture non-standard pipe size, but will have additional cost for it. There are some other considerations. One is for the welding requirement for pipe wall thickness. If your chosen wall thickness is between 10 millimeters to 25 millimeters, it's a comfortable wall thickness for weldings. But if you have a wall thickness less than 10 millimeters or larger than 35 millimeters, it is really good to check the welding teams, because it may be challenging for them to weld very thin or very thick pipes. And also sometimes you have the pipe wall thickness for forgings. Forgings are normally not designed according to DV codes, but more like SME code. And this wall thickness for forgings will be normally larger than the pipe wall thickness. So typically, like for bow head, pick launcher receiver pipes, anchor flanges. So it is recommended to design these items earlier for procurement, and some of the items you can put as line pipe procurement. And the last point is like the wall thickness for bucklings. For deep water projects, the wall thickness may be selected thicker, since most of pipe capacity has been taken against the collapse. You don't have much capacity left for bending moment or actual force. This is also a consideration for deep water projects. Okay, this is the last slide. Thank you for listening to this course. And if you have any questions, just contact me. And this is a contact email from my company. I'm very glad to receive your inquiries. I'm very passionate about pipeline design, and I also have a lot of experience on the wall thickness selections. Thank you.